Okay, picking up where we left off, we're going to move on to some trig. Okay. And this is a building process. So the only thing we're going to do today is sine and cosine. That's it. And we're not even going to derive that. I'm just going to, this is another one of those rare instances where I ask you to just memorize. So flashcards, if you will, if you're a flashcard person. Okay. And we get to that. What is a derivative of sine? It's cosine. What's a derivative of cosine? It's negative sine. You will continually screw up the minus sign. Everybody does okay with the sine going to cosine and cosine going to sine. Okay. Those are called co-functions, by the way. Where people screw up on is the minus sign. Okay, so make sure you copy it down correctly. What we're not going to do is derive that. I'm not going to explain to you why that is the case. To be honest, I don't even know if I could do it right now. Okay. So this is just another thing that, one of the few things that, like I said, they memorize, put it on a flashcard, put a box around it in your notes. And then we're going to take those two simple derivatives and incorporate them into some of the power rule stuff we've done. So we get something like this. What happens when you put a constant in front of it? Well, like we talked about on Wednesday, it doesn't matter. It's just a derivative times 2. Okay. Notice again the notation, y goes to y prime. If it's a 1/2, who cares? It's still a constant. You get 1/2. Again, this is fairly simple, but we'll continue. All right, this one maybe not so simple. What's the derivative of x plus the cosine of x? Anybody?
Is it 1 minus sine x?
Bingo. Good. Again, because remember, the derivative of a sum or a difference is the derivative of each individual piece. The derivative of x is just 1. Okay, because again, a linear term goes to a constant, which is the slope, and then the derivative of of cosine is negative sine. Okay. Now, second thing that a derivative represents, this is exciting, called a rate of change. And you're going to hear me say it 1,000 times, and eventually it'll burn into your brain. But a derivative represents 3 things. The first thing is the slope of the tangent line. The second thing is a rate of change. We'll get to the third thing by the end of the slideshow. Okay, so what's a rate of change? Well, it's a rate of change. You've done 1,000 things with rates of change. Miles per hour, gallons per minute, blah, 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 wide variety of fields, so growth rates, production rates, water flow rates, velocity, acceleration. When we wrap up with the first part of Chapter 2, we'll transition into something called related rates. I love related rates because they're all real-world problems. Okay? Like, for instance, you have a pool in your backyard, the spring rolls around, you want to fill the pool. We can calculate how long it takes to fill the pool, if you know a couple things. You're draining the pool in the fall. We can calculate how long it takes to drain the pool. Ladder falling off a wall. Okay, how fast are you going when you crash to the ground off the ladder? Most of them deal with like death and destruction, but we'll get to that later. Okay, but all of these are based on rates of change, and the rate of change compares one unit to usually a time unit. Okay, miles per hour, gallons per minute. That won't always be the case. Okay. We deal with something called a position function, which is fairly common. A position function is where something is located in space at a certain time. And by the way, for a couple minutes, just put your pencil down and watch. Okay. This is just, let's call it fluff. It's just a little background on how rates of change work. Okay. So it gets us to this I commonly call that the dirt equation. Have you heard that term before, the dirt equation from physics? Distance equals rate times time. I just rewrote it. Rate is distance divided by time. Okay. Miles per hour. The calculus, however, has 2 components to it. which is going to lead us to our third topic for derivatives. So we're going to skip this problem because we'll do something more interesting in a second. But I want to get to blah, 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 this. Okay. If we take delta S over delta T, the change in position over the change in time, we get something that's called average velocity. Okay? And I might be oversimplifying this, but the difference is this. If you leave your house and you drive to grandma's house, and grandma lives 100 miles away, and it takes you 2 hours to get there, you have an average velocity of 50 miles per hour. Everybody's with me, right? Now, does that mean that you leave your driveway doing 50 miles an hour, and you come screeching into grandma's driveway doing 50 miles an hour, and everywhere along the line you're doing 50 miles an hour? Absolutely not. It means that the average velocity over the entire trip was 50 miles per hour. Okay, so obviously when you back out of the driveway, you're actually going negative velocity, and then you accelerate, and there's physics involved there. From a calculus standpoint, what that represents is the slope of the secant line. Change in position over change in time is the slope of the secant line. We will do some calculations with that, and it's kind of important, but what we care more about, skip this, blah, blah, blah. Okay, hold on, I'm getting there. 1 second. Yada, yada, yada. Okay. What we care more about is the instantaneous velocity. Okay, you start driving to grandma's house at noon. How fast are you going at 12:25? So it takes a little snapshot in time and says, okay, how fast were you going at 12:25? Well, we were doing 75 miles an hour. Okay, flying down the interstate. Now, does that example make sense to everybody? Yes? Hopefully it's pretty simple. We're going to deal mainly with instantaneous velocity. The instantaneous velocity is represented by the slope of the tangent line. So notice I put the limit in there. Without the limit, which is just that difference equation, you know it as f of x plus delta x minus f of x all over delta x. That's an average velocity. When you take the limit, at that time, you get an instantaneous velocity. And we're talking about velocity. And so, as you remember from physics, velocity can be negative, it can be 0, and it can be positive. Speed, however, is something different. Like it says, it's the absolute value of velocity. Speed is always positive. All right? Questions on that? How many of you knew this already from physics? Raise your hand. Okay. There's a couple things that are going to get tricky here, and that is being careful that you read the problem to find out, do they want an average velocity or do they want an instantaneous velocity? Average velocity is just a, change in distance over change in time. Instantaneous velocity, you got to use some calculus. Okay? All right, so let's put this into play. In physics, I think, if I remember correctly, you usually derive this equation. Is that an accurate statement? Doesn't happen very often in math. However, I do want to give you a general term, or a general equation here. Actually, hold on. I lied. Stop it, Reedy. Learn to use the technology. Does that equation look familiar? Acceleration times the time squared plus the initial velocity times time plus the initial position. Okay. So if we apply that to this, what does it mean? Well, the acceleration there is the acceleration due to gravity. It means that person has an initial velocity of 16 feet per, I think we're doing feet per second here, which means they jumped up. And then 32 means they're starting from a height of 32. for the most part in math, they're going to give you this formula S of t. Occasionally, you might need to figure it out on your own, but if you remember this chunk of information, you'll be okay. All right, so a person's on top of a diving board, they jump up, and boom, they hit the water. So part A, when does the diver hit the water? So when that diver hits the water, what's true? What do you know? When they get to this point in time, what do you know?
The displacement is 32 feet.
No. I understand why you would say that, but we're measuring this as 0. They started at 32 feet. So they started with an initial displacement of 32 feet. However, did you mean their displacement from the starting point?
Yeah.
Yeah, you're right then. Their displacement is 32 feet. Okay. What else do you know? What's the height when it hits the when they hit the water? I don't think we've determined a gender on this. I'm sorry, what? Once more, I'm sorry, I keep talking over you.
0.
0, right. So the height when they hit the water is 0, which means 0 is equal to negative 16t squared plus 16t plus 32. Okay, solve that, please. I don't care how you do it. If you're smart, you'll pick up your quad formula on your calculator, or you can factor that quadratic, or you can do it a lot of different ways, but whatever, tell me what t is.
-1 and 2.
Not that we don't trust Marcus, but can somebody confirm? Okay, got a thumbs up. Good. Hey, Marcus, which of those answers doesn't make any sense?
The -1.
Right.
Time can't be negative.
Right, because we're not driving a DeLorean.
Yeah.
Anybody get the reference? Anyone? Prasant, what's it from, buddy?
Back to the Future.
Yeah, okay, just checking. I didn't know if that's in your wheelhouse. Okay, so t equals 2. It takes 2 seconds for that person to hit the water. Okay, and an indication of that is the word when. So you're solving for a t there. Okay, what is the diver's velocity? Okay, so this is where we get into some calculus now. This first calculation has nothing to do with calculus. That's just a simple physics / maybe algebra 1 problem. Now we get into this because we need to find a velocity. Am I looking for an average velocity or an instantaneous velocity?
Instantaneous.
Correct. Could we, however, find the average velocity? Yeah, they went 32 feet in 2 seconds. So we have an average velocity of 16 feet per second. Okay, but we want the instantaneous velocity, which involves a derivative. Okay, so S of t is equal to, the derivative of S of t is equal to v of t. Because that's what we did, in case you missed it, here. Okay? Velocity is the derivative of S of t. All right, what's the derivative of S of t? Again, we're not doing the limit process here. We're using the power rule. Make your life easy.
-32t plus 16.
Perfect. Okay. And again, there's physics going on here, there's calculus going on here. So at any point in time during this experiment, during this dive, that person's velocity, instantaneous velocity, is given by this equation. Okay? The time we're concerned about is 2. Therefore, what's v of 2?
Negative 48.
Now, 2 things. What are the units?
Feet
Feet
per
per
second.
second.
Good. And does that bother anybody? Or is that a good thing? Should that minus sign be there?
Yes.
Why?
Because he's traveling down.
They.
That.
Come on, it's 2020,
Yeah, they're
Max.
gone.
Let's go. They are traveling down. We don't know.
But they're traveling in the downwards direction.
There you go. Well said. Okay. All right, just for giggles, let's see what your physics knowledge is here. What's the derivative of the velocity called?
Isn't that acceleration?
I'm sorry, both 2 people talking at the same time.
Acceleration?
Acceleration, right. A of t. Which also means, we're getting a little crammed up here, that the acceleration is also known as the second derivative. It's the first time we've seen that. S double prime of t. Take the derivative of s of t twice. And I don't want to do too much with this. I just wanted to focus on the acceleration, or sorry, on the velocity, but we should also understand what the acceleration is. And we'll get to that a little bit more as we delve into these problems. We know what the acceleration is. If I take the derivative of this velocity for this particular problem, the acceleration is going to give me negative 32 feet per second squared. And for those of you, have you all had physics, by the way? Or are you currently taking physics? Which one is it? You all had it, right? I don't remember.
I'm in physics.
In physics now. Okay,
I think.
so you might have gotten to this already, but this number should look familiar because that's the acceleration due to gravity. Okay. Or you actually might know it as, I think it's negative 9.8, which is probably what looks a little bit more familiar because that's meters per second squared. Okay. So in a real world problem like this where you're jumping off of something or you're dropping something or you're throwing somebody or something off a cliff, this acceleration will be the same number over and over again. It's always that negative 32 or that negative 9.8, depending on what units you're working with. Common mistake with part A is people want to set the velocity equal to 0. Okay? We don't care about where the velocity equals 0 to find that hitting point. What's relevant here is the fact that the height is 0. When I set the velocity equal to 0, I'm actually going to get 2 spots. I'm going to get something down here, but, whoa, sorry. Come on, ready? But I'm also going to get that point up there, because for that fraction of a second, that diver will hit a 0 velocity and then start to drop. Okay. Questions? All right, so, looks like I did all the work. Okay. Notice that solving that quadratic, I factored it. If you don't have the quadratic formula on your calculator, you should have it. Does anybody not? I think I asked you this question already, but I'll go through it again. If you don't have it, if we were in the classroom, well, you could either wait till you're in the classroom. If you're coming to the classroom, you all got that email, right? Okay, so I'll get to see some of your bright, shining faces in person. I can give it to you then, or if you just search quadratic formula on TI-84, you'll find a program that you type in, you're good to go. But it is something you should have on your calculator. Okay, we did all that, solved that, negative 48 feet per second, great, okay, we did that. We're done.